Okay, so I thought it would be nice to actually just make a recording of this presentation. So this is the presentation that I gave for my master's thesis defense, and it's kind of nice because it gives a little sort of outline of the type of research that I do and the type of work that I'm engaged in, my PhD work, and subsequently also the work that I do in my own laboratory is all sort of centered around this subject, and I use a lot of the same equipment and tools in my lab as I do at the university. So this is sort of an outline of the work I've done at the university, and this was presented in May of this year when I defended the master's. So the presentation was called Femtosecond Laser Micromachining from Conception to FBGs. The title of my thesis is a little longer, and I just can't quite remember it right now, but it was chosen to be long just sort of for fun. What you see in the background here on the left side is actually a picture of the very first piece of material that I ever machined on the micromachining system, and that was basically just a piece of fused silica wafer that I taped down to the stage and scanned the laser system across just to see if I could damage it. And I thought the picture was pretty cool, so I included it, and that was really the pretty big highlight for us at the time when I got all the stages working and all the optics down on the table and the cameras and imaging setup was all running. So that was a very exciting time when we got that operational. In the middle, you can see when I'm running the system with the second harmonic. So that's 520 nanometer green laser light. Most of my work right now I'm using 1040, which is the fundamental of the ultrafast laser we have in our lab. But sometimes I'll operate it at slightly higher frequencies, and we'll see that different wavelengths. We'll see that a little later when I talk about the OPA that we have for our system. So, quick outline of what I covered. I'll start by sort of motivating things a little bit. Basically, what are fiber Bragg gratings? That's a big component of my research. What are the different sort of laser refractive index modification regimes? We really just talk about two. We call them type 1 and type 2, and I'll characterize those basically based on temperature stability. And we'll talk a little bit about why we started with FBGs. Really, the answer to that is that it's just a good device to work with. It gives us lots of information and feedback about sort of the properties of our system and our capabilities and our precision. I'll discuss the sort of overview of the micromachining system, laser and the OPA, the optical layout, the stages we used, the equipment that I had to build to set this entire system up, because when I joined the group we didn't have any micromachining platform, so I had to design and build everything from scratch, and the jig, which was a pretty big modification we made later on, which resulted in a lot of improvements. And I'll go over some of our results from my master's thesis. There was no publication that came from this work, but the master's thesis work definitely laid the groundwork for a lot of research we're doing right now, and future publications we're going to get out hopefully in the next few weeks, actually. That'll be sort of late October 2024 if you're watching this in the future. So hopefully we'll have some work coming out of this very, very soon. It's just taken us some time to get into a position where all the equipment is in place, and we've gained some momentum now. So I'll talk about FBGs with both the laser fundamental and the OPA. OPA is optical parametric amplifier. Basically, it lets us extend the wavelengths of the laser. And I did a little bit of testing with waveguides, but we didn't do any waveguide characterization. And we'll discuss some what next opportunities and what kind of experiments we're looking at doing. And this has changed a little bit since May, because over the summer we were doing a little bit of work in nonlinear optics rather than just in purely laser inscription. So there's going to be maybe some different outputs than what this would suggest, but these are still valid avenues we'd like to explore. So motivation. What are fiber Bragg gratings? So fiber Bragg gratings are basically they're a structure that we inscribe into the core of an optical fiber. And that's demonstrated, I think, pretty well sort of over here in this lower left image in figure 1.1. And basically what we have is we have this optical fiber here, and what we write into it is this sort of periodic modification of the core. So if we think that the black region here that I'll highlight in red, if these black regions are where the laser beam damages the glass, that creates the periodicity which is given by the Bragg equation, which is m lambda b equal to n effective capital lambda here. And really the capital lambda, this is the pitch of the grating, and the pitch is given by this equation. M is the grating order, and n effective in optical fiber is around 1.447. So really what a Bragg grating is it's a nice optical filter effectively. And if lambda BBS is the broadband source, so effectively a broadband source would look something like this. And for erbium, that's centered around I believe 1550 nanometers, and it's maybe goes from 1535 to say 1560 or so out here. Just depends really on the source and amplified spontaneous emission source. So what this allows you to do is if you inject this signal into the Bragg grating, what you'll get back out is the lambda b, and lambda b will look something like this. And the transmission source, which is lambda b or lambda broadband minus lambda b, will look something like this. And that's what we see over here on the right. We see the reflection spectra, right? This is here at some lambda b. And then we have the transmission spectra here over at some lambda b. And actually, I think my slide deck will show in just a moment what this actually looks like. So if I erase all this real quick, we can see, as I click forward here, what that actually looks like. So for an FBG resonance at 1550 nanometer, in the first order, the pitch would be 535.74 nanometers. And so obviously we're starting to see here very quickly that we need to hold precisions that are very, very tight. So this is going to become one of the major challenges of this thesis, is designing a system that can move these distances very precisely. So in second order, we're going to be looking at 1071.48. So basically, as long as you're some integer multiple of this pitch, you will still generate a resonance here, and that's because the refractive index modification in the core of the material is more of it's more of like a delta function rather than like a sinusoidal modification, so it has higher order Fourier components. And so even though we're at the second order multiple, we're looking at that's what this grating is written in, what we're looking at is actually the second order resonance, not the fundamental resonance. The fundamental resonance of this grating would be at half the wavelength of 1550, so 775 or so. So it's kind of a convenient thing. So the actual fundamental reflection spectra and transmission spectra would actually be probably a lot stronger than what we're observing here, because the second order resonance will be slightly reduced in comparison. Of course, this is a very high order overview of this. There's lots of great books out there that describe sort of how Bragg gratings work and sort of couple mode theory, describing how the mode and the core interacts with the actual grating structure. So when we're writing the grating, what happens is this reflection spectra would sort of start as a flat line here, and it will start to sort of grow vertically. And as we write the grating longer, so we increase the number of planes, so the number will start with sort of 1, 2, 3, and we'll build up to thousands of them, line by line, piece by piece. This resonance will grow up and it will shrink, and in transmission you will start to see that it will start to reject some of the wavelength in this region, so it'll start to drop down, and it should get narrower as it gets longer. So that's really what we're looking to do. We're looking to have very, very deep resonances, which in this case, I think this is greater than 25 decibels of rejection. So I think that's 99.95 or something percent reflecting. And we want the resonance to be very small because that gives us good wavelength selectivity. and it allows us to concatenate multiple sensors in a single array in a sensing application. So these are very advantageous parameters to have. So type 1 and type 2 index change. Really, there's a little more nuance to this than what we actually describe here, but in principle, we're going to just characterize it into two different types. And type 1, imaged here on the right, is due to nonlinear absorption and generally considered to be color center formation and destruction. So that's sort of, I believe that's basically breaking sort of the symmetry of the structure inside of silica. So the glass structure is modified, and I believe they call that color centers. And it's generally considered reversible by annealing. So if you heat this up to higher temperatures, typically sort of below the 900 C range, this structure will erase when they're ultrafast laser induced damage structures. And usually we consider this a smooth index modification. So it doesn't have any fractures or voids in its profile. Type 2, on the other hand, is sort of the opposite of this. It's triggered by material ionization, and much higher energy from the lasers required to produce type 2 compared to type 1. And it has a much sort of rougher index profile. If you zoom in closely, what you would notice is generally there'll be lots of cracks or voids or sort of like micro cracks that are in the structure of this modification. And this is generally consistent with things like nanograding formation, and it generally is temperature stable up to very high levels. Usually you have to bring this up to the glass transition point of the material to erase these devices. So that's the high temperature stability, typically over 1,000 degrees. And it's also consistent with strong scattering. So here, imaged, you can see actually red light from a red laser diode coupled into the fiber scattering off a grating. I believe this device was written to be about 2 millimeters in length. Although I'm not 100% sure the exact length of that device, but I would say around 2 millimeters or so. So there'd be a couple thousand grating planes visible in the brightest region here. So often we would sort of ask this question, why would we even want to start with FBGs? And really, the reason we want to do that is because it matches the background. I have some experience based on previous work I've done in academics with Bragg Grading inscription, and my supervisor also worked a great deal in this field in the past, and it was just sort of the right combination of skills to sort of to have a target thing that we're going to work towards when we built the machining system. And so really, it allows us to qualify our sort of system performance and capabilities so that we can demonstrate this to collaborators and partners and sort of generate a sort of a basis of what we're going to do for our research going forward. What we really care about is precision. Accuracy and precision is really good. Accuracy would mean effectively that whatever wavelength we design that we want to be writing at, say 1550 nanometer, we hit that right on. This matters a little less. We more prefer to have high precision, because precision is what governs how closely each plane is spaced from the other relative to its position it's supposed to be in. So we want those planes to land at exactly the pitch that we designed them to be at, and if all the pitches are sort of systematically off, or there's a slight accuracy error in the width of the pitches, that's okay. We just want to make sure that they're all very precisely positioned relative to each other. So this is important for generating very narrow grading resonances, very narrow grading line widths. And so we managed to achieve that. And what this little figure down here shows, actually, where we have this green block where it's written fiber core, this is basically the readout from our control software, from our control system, and we're using Aerotech stages and controllers. We have an NPAC system, and the software is A3200. And in A3200, you can plot the readouts from the position errors and velocity errors. And what we decided was that it was very difficult to tune the stages such that we would eliminate this sort of initial movement error. and the settling time is sort of given at say 50 milliseconds. And so what we decided to do was make the grading plane long enough so that when we write through the fiber core, we're sort of writing at the center of this motion or this time period when the laser is on and when the axis is moving to scan across the core. And what that means is that effectively our position shouldn't have any errors in it that are introduced by the positioning steps in the control script. So a little bit of time had to be taken to figure out how to get that to work correctly. And starting with FBGs sort of gives us a way to get some feedback while we're tuning the system, and that's sort of what I was just talking about, where we have to be careful about this position error and our settling time. And if we can get the system tuned very well for these very small, 1 micron steps, so that we can move 1 micron and step and settle in, say, less than 50 milliseconds, this is pretty tight performance characteristics for servo loops, especially when we're dealing with we need to hold tolerances to the order of plus or minus 5 nanometers, 10 nanometers usually. If we can get better, I would love to get better, and sometimes we can. Just depends on, honestly, the time of day. Buildings and vehicle motion on campus during the day can introduce a little more noise than, say, in the evening. So actually it's beneficial to be writing tests in the evening if you need very high performance characteristics. But we did manage to get our position errors quite small, even in the on the order of 10 nanometers. And the y-axis is the critical axis. That's the axis where we're actually stepping along the fiber core length, which is the axis that's actually defining the pitch of the grading, basically. So FBGs are very useful optical devices and sensors as well. So this is really why we motivate by starting with FBGs. It sort of gives us a thing that we can make, that we can measure, we can characterize, and it gives us feedback on the performance of our motion system and our motion platform. And of course, they're very useful, so we can use them for future projects. Another nice thing about FBGs, yeah, that's true, is that we can use them for looking at the index change characteristics and behaviors, and we can sort of roughly calculate the degree of index modification based on the strength of the grading that we write. So a really big part of this thesis was actually building this system. We didn't have a lot of hardware when I started out. We had the laser, which was the most important part, the hardest thing to get. And so what we actually have is an industrial Spectrophysics Spirit HE, and this is the 1040-16 model. So basically at 200 kilohertz, it produces 16 watts of laser light, which corresponds to 120 microjoules of energy, which is actually quite a lot for laser inscription, but it's good because it allows us to throw away a lot of that power if we don't need it, and allows us to pump an OPA, which we'll talk about in just a second. So the wavelength is 1040 nanometers. It's a ytterbium tungstate-based system. I believe it uses a fiber seed, but I'm not actually completely sure on that. It could be just a solid-state seed and then an amplifier. It's got about 4.5 nanometers of bandwidth. 350 femtosecond is what the laser specs. It's actually around 280. And it runs 16 watts at 200 kilohertz, as I said. And it's designed for this sort of industrial machining application. So exactly what we're sort of using it for. And they're also quite often now used in research. But they're really nice because they have a single box controller and cooling. It's all in one. We don't have to worry about a big tabletop amplifier and aligning the system and tuning it. So it's very convenient in the sense that you sort of just plug and play, and it just works every day when we come into the lab. The other component we have is we have a Spirit OPA. I believe the Spirit OPA is actually a light conversion OPA. It's just branded by Spectra. And here we see the tuning curves for it. So we can get down to, I believe, 640 nanometers on the signal. Yeah, that's right, 640 to 1040. But the efficiency drops off right at the 1040 mark pretty substantially. That's 190 to 200 femtoseconds. So we pick up a bit of bandwidth on the shorter wavelength. We get a little shorter pulses, and similarly in the idler, we still pick up a little bandwidth, but we're limited a bit by the wavelengths we're working at. And so the idler is around 1040 to 2.8 micron. In reality, I think it actually goes a little farther than 2.8, but so it gives us almost right up to the edge of the mid-IR, and so there's some things we'd like to do in the future looking at sort of the different regimes, whether we're using long wavelength versus short wavelength. This will change the number of photons required for ionization. It might also change the mechanism by which we're forcing ionization. So there's lots of cool stuff we can look at. And it too is also single box. So the actual optical layout of the apparatus I built is shown here. This is all built on a 4x8 foot table. And this is sort of a top-down view. And we don't really get to see the structure of the gantry, but this is actually sort of sitting, the gantry is actually sitting vertically. So if we were to sort of draw a picture here of the side of the table, okay, here's our legs on the table. The laser is over here, and the OPA is right beside it. Sort of, they're different sized boxes. And then we have our big gantry sitting here, and then we have our stages and platforms sort of sitting here. Not a very good picture, but basically the beam comes in this way. There's a big objective lens here, and it's all sort of bolted to the front of this gantry, and the laser beam comes out this way, and is routed through some optics, and then up to the system. So this is sort of what the actual overall setup looks like from the side, and I believe there's a picture later in this presentation, so you'll see that in a little bit as well. So basically we have the spirit, we have the OPA, and there's some beam routing optics. So here we have some beam cubes so that I can change whether we're pumping the OPA or whether we're taking the spirit beam directly and routing it into the machining system, or if we're routing it to some other experiment that we're working on the rest of the table. So what we have is, if the beam is routed, let's say, directly to the spirit, which is what we tend to use quite a lot, we have a wave plate and polarizer to attenuate the beam. We steer the beam around. We have a few apertures to maintain alignment, because the OPA is pretty good in its output alignment, but sometimes the beam does drift a little bit when you change wavelengths between signal and idler, so you have to do just some small tweaks in the beam positioning to get things lined up in the optics, keep things consistent. We have a neutral density wheel to have some more fine control over the pulse energy here, and it's also because the neutral density wheel allows us to control the broad bandwidth of the OPA compared to the laser. Our waveplate polarizer combination as an attenuator only really works for the spirit, doesn't really work for the OPA. So we have this here, some more apertures to maintain beam alignment. There's a Galilean beam expander here. This turns out to be actually incredibly important. So this component right here, this beam expander, really, when you're working with materials on the jig, so that's kind of over here, what you actually have is you have sort of the optical fiber, and the fiber is sitting on, say, a piece of glass, and there's a cover slip over it, and the cover slip has some, thickness, and there's index matching oil in this area, right? And what happens is when you're focusing into the fiber, this material, so this cover slip and the oil, and there's usually some sort of distance between the cover slip and the top of the fiber, all of this actually causes some chromatic aberrations, some aberrations, phase front distortion, which means that the actual focus, instead of being maybe very small where the index modification is occurring, it actually tends to be distorted quite a bit, so your index modification volume can change quite a lot. And so this can make controlling the type 1 versus type 2 damage, so whether it's smooth or whether it's very, very violent and rough damage, can make controlling that very difficult. And it can make this damage region, actually, sometimes it can be much greater than the diameter of the fiber, which means what happens is you blow the coating off the either side of the optical fiber. And we want to keep the coating on the fiber because it maintains the fiber strength. That's one of the advantages of writing with femtosecond lasers. So to avoid this, we have to make sure that we set the beam either to be slightly diverging or slightly converging to compensate for the thickness of all of the material prior to the focus in our actual setup that we're focusing through. So that's was a very big key takeaway of this thesis, was that we needed to sort of have some compensation for that in here. So that's kind of where we are. And then we route the beam through a few mirrors and up through a periscope up onto the top of the gantry. So that would be sort of like the laser beam comes along here and it bounces off a mirror and is routed up to this way. And then there's sort of another mirror here which bounces it away sort of down towards the actual optics on the machining system. And so that routes into here, and then we actually have another beam which then sort of forces the laser light down into the table right about here usually. There's the rest of the optics are here, and then there's the CMOS and OL means the CMOS camera and objective lens. So there's actually a mirror built into that assembly to use imaging simultaneously while we're inscribing the gratings. And I have a video later that you'll see which shows that. Yeah, so this is just the sort of the wordy version of the written version of what I just said, and of course the XYZ stages is the stack up of Aerotech stages. So the stage we actually use for this work is the ALS 130 stage, and in theory these stages have a minimum incremental motion of 1 nanometer, which you can sort of see, but in reality we're typically stepping on the order of about 1 micron. So if we can hold a precision to around 10 nanometers, that's just pretty well within the range of the capabilities of these stages. So they use linear servo motors, and that's this sort of linear track here, and then there's this sort of forcer where there are coils. And it's I believe it's a 3-phase motor effectively. This is the way this works. And then we have a grating basically, and a little laser light source and a photodetector, which forms the optical encoder, which is what actually reads out this sort of 20 micron pitch in this grating. And then in software, I believe there's a 16,000 times multiplication that we can put onto this, which gives us roughly a 1 nanometer resolution. And in fact, Aerotech can, in theory, go even higher than that, but I believe the minimum resolution is still limited to 1 nanometer. I forget how the specs work on that, but this can be looked up in their specs for the stages and the controllers. So this system was actually purchased used. So what I ended up doing was I called around and I found a supplier in the US of used sort of fabrication equipment they mostly deal in fab surplus for making integrated circuits, but they had a couple of these stages and controllers that I think were used for making, they were laser welding systems for packaging indium phosphide, I don't know, photo receivers or transceivers or something like that. And they had been bought surplus from some asset auction or something like that. And so I managed to get all the stages and controllers for about $4,000 US. And this hardware would probably normally run you, I would say 60 to 70,000 Canadian at least, maybe the similar in USD. It just depends on the day and where you get it from. So we had a pretty substantial savings when I found this hardware. Now this stage is taken apart because it actually had the cross roller bearings were damaged in one spot, so the stage actually clicked. It had a sort of like a detent in the middle that was causing problems, so we had to buy a replacement stage, but also we bought that used as well. So we managed to save quite a lot in building this. And so here's actually a picture of us dragging it through the university. We had to pick it up from, it was delivered to the university on a pallet. We had to pick it up and drive this thing across the university. Through all the hallways, and then once we finally got down on the table, I dismantled some of the original system configuration, and we sort of had to just work with what we had. So I had this great big riser block, that's this thing down here, and that's actually a little too big for what we want, but it's what we had, so it's just what we had to use. And I had to end up using it because if you can see here, there's a bit of a pigtail that sticks out at the end of this stage, the Z-axis. And the only way that it could be used is if it was bolted vertically like this on this riser block, just with the way the cabling sticks out of it. So rather than remachine all of this and refabricate it all, I figured, oh, well, we'll just use it exactly as is, which in hindsight was maybe a slight complication in the long run. But I remachined the mounting plates and bolted the whole system together. And here it is, the very first time it was set up and placed on the optical table. And in reality, we had to drill, we had to Swiss cheese this thing. It was way too heavy. And then this axis is the critical y-axis. So this one is x, this one is y, and then this one is z. This was actually too much mass on the y-axis to get the settling times and the precision we needed, so we had to put it actually up on top of this platform, which I think we will see in a later photo. So an important aspect of this is tuning the PID loops. So system PID loop tuning, really, I won't get into it. There's lots of tutorials online about how this works, but basically we started with Aerotech EasyTune, which is sort of a built-in tuning software. It's slow, inconsistent settling time is sort of what results, but it will make sure the system is stable so it doesn't have like resonances that will cause problems with your machine performance. And for a lot of applications, this is perfectly acceptable. But for us, it's not. So we can't use the automated tuning system. We have to manually tune it. So to manually tune it, we have to understand a few different characteristics. When the system is underdamped, so our various servo loop parameters, the PID loop parameters, are forcing an underdamping condition, it's going to oscillate around the target position and take a long time to reach a steady state when we do motions. This is bad because when we step 1 micron, we don't want our stage jittering back and forth. It's going to produce wide grading planes and inconsistencies. And you can see that it's very inconsistent depending on the direction it goes in. Some of it's positive air, some of it's negative air, and it's oscillating. We can also enter an overdamped condition where it settles to the position very rapidly, but then it's unstable in that position. So that's what all this jittering and noise is all about. And then when we have a correctly damped scenario, we have fast settling and we have stable in-position holding, which is essentially what we see here. And this is really what we're going for. And there's a little more behind the scenes than this. We also have to sort of set some filters to sort of prevent these system resonances from occurring. And this is actually a very complicated bit of work. And this took probably the better part of 2 months to figure out how to get the system tuned so that we could get the performance characteristics we needed to write these gratings, both quickly and efficiently, but also precisely enough that we got the results we're looking for. And I think a lot of groups don't take the time to go through this, just because of how complex and how difficult this can be to do. But we can get excellent performance characteristics, and I can write gratings extremely, extremely quickly. We often choose to write them slower just because we're doing research and we want that. We don't really care about having, high production throughput, but it is possible to achieve, a grading inscription in the order of, when you're writing line by line device, in order of 2 to 5 minutes, depending on how well you tune things. Of course, point by point is almost instantaneous because you're free running the laser, but this is just there are advantages to writing in line by line that are not demonstrated in point by point. So anyways, that's just why we chose to do that. And so we go back to this idea of this is why we wanted to have the grading plane length be as long as it is, so that as we pass through the fiber core, we've settled all that error in the y-axis out. We don't care so much about x-axis errors, but we do care a lot about the y-axis errors. So another thing I had to build is the gantry. That's what holds all the optics in the vertical axis. That's what mounts our camera, that's what mounts our lenses, and routes the laser beam down to the actual setup. So to do this, normally you would buy something made out of granite, because granite is very thermally stable. It doesn't vibrate a lot. It's very stiff. Granite is too expensive, and I didn't have the time to wait around for it, nor did I have the interest in designing the granite and ordering it and all this. So I said, why don't I just make something that's a close approximation of granite? So I did the calculations for the thermal expansion of aluminum and for concrete and for stone and natural granite, and then of course granite that's there's another material called like synthetic granites, which are made by combining stone and epoxy together, which is used in a lot of applications where they'll simply cast the granite-like material and it has the same properties effectively. But what I chose to use is ultra high performance concrete because it was relatively cheap and easy to make. I could mix it in my garage and I could buy all the components locally. So effectively we need Portland cement, which is the binding agent in concrete, sand and fine aggregates, so I can buy sand and stone from a local hardware store. Super plasticizer, I believe this is sodium silicate. I don't remember exactly what that material is, but basically this means that you can put in water and the mix will basically look dry, but the super plasticizer, as you continue mixing, will eventually cause wetting of all the materials, and you can use a lot less water to make the concrete, even though it will still flow. So super plasticizer is important because the less water you have, the harder this concrete will be in the long run, which is we really want. We want really hard concrete. And we include fiber additives for additional strength, basically. So here's the mix proportion I used. You can see there's binders, cement, silica fumes, sand, gravel, water. Water and aggregates is another important component. And of course then we have our additives, which is our super plasticizer. So that's the typical mix proportions, and we modified this slightly for our application. And I included basically fiberglass as an additive to increase the strength. And it was low cost, fast and easy to build and test. So basically I got some wood from the hardware store and I fabricated a set of forms in my lab at home and then welded up an internal structure. So they needed to be mounting points to bolt. This here is sort of the top component. That would be this part here. And these are the posts. So this would be, say, 1 and this is 2, and this is 1 and this is 2, and this would be 3 here. And so what you see here, this component is this hole here, okay, which is actually in here. And this is how we bolted this top part of the gantry down. And there are mounting points on each of these, basically cast into the concrete. And that's what this is here, this point. And I believe you see them right here. And that's what these are. And so that's how I could bolt the aluminum breadboard plates, which I had to custom machine. So we ordered them from Thor Labs, and I custom machined them to fit this. So the gantry, the concrete gives us the strength and the thermal stability, and the aluminum breadboard gives us basically a mounting point to work with. Now you could argue there's some thermal expansion, to the aluminum, and it's going to cause the mirrors to shift, this, that, and the other. In reality, it doesn't actually. Our lab is not super temperature stable. It probably swings 5-10 degrees day to day. Well, maybe not 5-10 degrees, but there's enough temperature instability in the lab that you would think it would be a problem, but in reality it didn't. And I think in hindsight I probably could have just built the entire gantry out of aluminum, and it probably would have been fine actually. Because typical grading inscription takes an hour, and the temperature doesn't swing that much over the course of an hour. So we're not usually ever working on timescales longer than that, and sometimes we work even faster. Sometimes we're 5-10 minutes on an inscription or a test. So as long as we maintain stability on this window, very small couple micron adjustments in between inscriptions really doesn't make much of a difference at all. But that's just a component we had to build to build this whole setup, because we simply couldn't, the budget was not available to buy it all at the time. So if I wanted to be ambitious, I had to build everything. So the first thing another component we had to work on was building this jig, and so this is what actually holds the fiber for inscription. The first one was sort of, I don't know why I ever thought this would work. I had machined a piece of acrylic with a sort of a slot in the middle to hold the fiber, thinking that the fiber needed to be suspended in air and couldn't have anything sitting below it because I wouldn't ever be able to make anything flat enough to sit below it. This is sort of baloney. In reality, this jig, it never, it was very simple. It provided very light clamping, and it was not stable whatsoever. And basically, because of the design in here, the fiber was held between 2 points, and what it did is it formed a catenary. And so when we were writing, we might be lined up with the correct Z position here, but by the time we got some distance over to this point, this is where our laser is writing, is up in the air. And then as we continued writing, we would eventually walk back into the core, right? And so what happened is that we were getting terrible grading resonances. And I think also, if we look at this from this direction, right, what we're actually seeing is the fiber is here, but it's sort of doing this droop along its length, right? And when we look at this droop, this fiber is sort of drooping down. Here's the core, here's the core. This is like a 3D view, and this is at the end, right? We might be writing in the core here, but by the middle we're not writing in the core anymore. We're still writing at this position, and so we got these really terrible grading resonances. We couldn't figure out why. It was a number of problems. I think it was a combination of the collimation we were using, but also this mounting. So by the time we had sort of figured out the collimation part, we could get short distances of high quality grading, but it didn't work well. So I over Christmas I went home and I said, okay, well, let's rethink this, and I came up with this idea where basically now we actually have a flat platen, and then this is where the fiber is held, and it's actually a piece of glass, and the fiber sits very flat on this piece of glass, right? So this is the fiber sitting here, right, and it sits very, very flat on the glass. I can't draw it perfectly straight, but and it's actually just a microscope slide that I just machined into the surface of this plate. And there's a tiny little V groove that's on this side and a tiny little V groove over here. And there's 2 rubber clamps and magnets on either side. And these magnets are, I think they're about 100 pounds of clamping force on each side. So they're quite good. And there's one little Thorlabs dovetail stage here, which allows us to apply tension to the fiber. So this meant that I could clamp the fiber very tightly, and we could pull it very straight. And that's important. You want this fiber to be very straight along this distance. So once we figured that out, and we got the pitch and pivot and roll and yaw and everything all straightened away so that we could maintain alignment, I mean, now I can maintain the fiber. When you're looking through the microscope, what you see is here's the core and here's the cladding. If the laser point, let's say, was put here, you could move this 20 millimeters, and our walk-off might be in the nanometer range or less. Sometimes you get it right on the money and it doesn't walk off at all. So this is, we're holding tolerances of say 200 plus minus 200 nanometers across 20 millimeters of traverse distance. So we can write arbitrarily long gratings basically at incredibly high precision along this core. So, and this in SMF28, which is standard telecom, this is going to be about 8 microns, maybe 9 microns. I think it's 8.6 or something like that. So we can write in all sorts of different fibers, large core, small core, 4 micron for short wavelength sources. So we can do all kinds of interesting stuff because of that. So this was a very critical component that that I built, and I machined this, and really this was sort of the last thing that then unlocked our ability to write really, really, really high quality gratings. And so the completed system looks like this, and it still looks like this today. In the future, I think I would like to take this Z stage here, and I would like to actually put it on the gantry. And then the optics, the lens itself would then move. So this part here, the actual beam turning optics would stay fixed. And what we would actually move up and down is this objective lens. So the objective lens then traverses in and out. And this would be very useful because it'll allow us to sort of fix all of this, and this x-axis and then this y-axis, they can be put together instead of being separate. Right now they're quite far apart, and there's a lot of mass in this z-axis still. So we can eliminate all this mass on the x-axis and put it up underneath the y, and save ourselves a lot of errors in x direction as well, which would enable us not only to be able, because right now we can only really maintain precision in Y, and this one being X. So X, we can probably hold 300 nanometers, but that's not enough for gratings. And here we're maybe, we're less than 10 nanometers, basically. So if we can improve the x-axis a lot by rejigging the system or redesigning the system slightly, we could probably pick up the ability to write even more arbitrary, structures where precision in both axes is required. So that's kind of some future ideas. The translation volume is 100 mil by 100 mil in X and Y, and it's 150 millimeters in Z. We don't use majority of that. We typically are working in a volume of maybe 20 millimeters cube. There's about 100 kilos of concrete in this ridiculous setup, and we built a few custom machine jigs and components. And the X, Y, Z axes are defined as X, Y, and Z, as I just showed. So now the most exciting part is what are our results from this setup. So we wrote some fiber Bragg gratings. Saw some interesting appearance of damage that's confined in the core, and I think this is probably pretty obvious in retrospect, but when we first saw it, it was a bit surprising. The core is a lot more sensitive to damage compared to the cladding because the core has germania dopant in it, which I think basically increases the band gap, so we need fewer photons absorbed simultaneously to cause ionization or damage in the material. So it's just slightly more absorbing than the cladding is. So this is a top-down image of a grating that's been written. This is a second order grating, so the pitch is about 1 micron. This is a 90-degree rotation of it, and so you can see sort of the structure of damage when we have this appearance of type 2 damage. So this rough damage is a bit of type 2, and I think that the damage point, so the damage that's on this side is sort of the type 1 component, and the damage that's on this side is actually the type 2 component. And when we have type 2 damage, we characterize this by white light being generated at the focus. And I think we may be able to see that in this video. It's very difficult to see, but if you look very closely at this point here, you can see that when it crosses the core sometimes and when it's moving, there's a bit of flashing and flickering at that point. And that is effectively white light being generated at the focus. So if we have the energy set lower, what we're actually going to see at the focus is blue fluorescence. So it's difficult to see, but this would be the core in this image, roughly speaking, somewhere around here. And when we pass through the core, it seems that the germania dopant generates a slight blue fluorescence, and that's this point right here. That's where the laser modification is currently occurring. So we can kind of tell whether we're producing type 1 or type 2 modification. And this is, it's nice to be able to see this, and our imaging has even improved since then. The video was relatively blurry. Now we have very crisp, very clean imaging, so that we're getting better and better feedback, and we're getting better and better systems and procedures as we sort of continue to develop this hardware. So here's a device I wrote. We sort of set a benchmark. We said, okay, well, we want to achieve 20 decibels of transmission. That's important. And we said we want to have something around 200 nanometers of bandwidth at 3 dB point. So this is pretty narrow, 0.2 nanometers. Or sorry, 200 picometers. I think I said nanometers. And this is the resonance we got. So I think this was around 1,000 grating planes we wrote. And the centroid wavelength is 1548. I think the design was 1550, so we were slightly shorter. We were 2 nanometers shorter than I had anticipated based on my calculations. And our width, though, was much better. We had a width of 180 picometers. So we actually exceeded our target. The device is only 1 millimeter long, and so for a 1 millimeter device, we can actually calculate, although this is slightly inaccurate, this calculation, because it would be for a sinusoidal index profile. But as a rough estimate, we get a delta n on the order of 1.57 times 10 to the minus 3. So fairly high delta n along the grading plane. So the delta n would be, if we're to look at the modification profile, and we plot delta n, here's 1.5, the exponent of minus 3, and this is our pitch. Lambda is on the order of like 1.047 micron, I think. So this is what we're looking at, basically. And this is effectively the video I showed in the last page. And the gradings look pretty good. We've been able to improve these sort of side lobes and some of these errors we were seeing. We've been able to improve that, so we don't see as much of that anymore. We got smoother type 1 modification now than we did then. But still, this is a very good device. Means that we have very good precision in the grading plane placement. And we took this grading and we annealed it. Of course, this stuff stays, so let's just remove this for now. We annealed it at high temperature. And when we annealed it at high temperature, we found that initially, we sort of see that our grading has lots of noise in it, lots of little spikes and side lobes. And as we continue writing this or heating this up to, I believe this is about 1000 C here. Actually, it might be closer to 1100. That a lot of those components have annealed out. Now we have a nice smooth grading. And what I think's going on is, when you saw previously the damage point, we had a sort of a circular point and then sort of a streak of rough damage here. And this is sort of the grading structure, right? So what I think is going on is, this is our type 1 modification, and this is our type 2 modification. And if we remember, type 1 is not thermally stable, so this goes away, and we're left with the type 2. And when we anneal out the type 1, because there might be some error or some phase difference between type 1 and type 2 modification, we actually see that the grading gets cleaner. As we anneal out the type 1 component, we leave only behind the type 2 component of this grading. It was just an interesting sort of feature of these devices. The parameters we used for writing these gradings. The laser is always run at 5 kilohertz, 1040 nanometers. The numerical aperture is 0.55 for the objective lens. Its emitted TORU 50x. We always set the polarization to be perpendicular to the core, and our pulse energy is around 70 nanojoules. And we wrote 1,000 planes. It was a second order grading. The pitch was 1071.48 nanometers. And our x velocity, so that's, if this is the core, then our x velocity is this direction here, basically. So that's our x velocity, and then our plane length here, this one, was 30 micron, which is this number here, 0.3 millimeters. So that's sort of the grading parameters that we used. We did a little more work, and I won't talk too long on this because we need to come back to some of this work still and do some verification of these results. But we did a bit of work with the FBGs using the OPA, which is a parametric amplifier, which lets us extend our wavelength range. So we chose 750 and 1260, which is sort of on either, this is both in the signal and the idler band, just to try to be a little farther away from our fundamental at 1040. So because of a slight alignment problem with the OPA, I was running at 100 kilohertz instead of 5 kilohertz. But if we set the average power the same, so the pulse energy should be the same between both of these tests, and all conditions being held constant, we wanted to know if the laser wavelength impacts the inscription. And it seems to. It appears that the shorter wavelength will generate a stronger delta n, which would appear to be consistent with absorption being stronger for fewer photons. And so for the, let's see, for 1260, so this is the 1260 number, we have roughly 9.5 times 10 to the minus 5, so minus 5 order. And for 750 nanometer, we have 1.7 to the minus 4. So we have quite a bit stronger refractive index modification at shorter wavelengths. This is by no means a direct verification. We didn't have enough time to continue this work, and since then we've been focused on some other research work. So I would like to return to this, but some interesting things we saw was that typically the shorter wavelength appeared to produce rougher index profiles, whereas the longer wavelengths tend to produce a lot smoother profiles. So again, there's more work to be done here to understand exactly what's going on, and to ensure that the peak power and damage thresholds are kind of the same between both these conditions, to sort of see if they can be directly compared or not. And we did a little extra work with waveguide inscription just to demonstrate that it could be done with our setup and see if we can get smooth indexed profiles. So we used 150 nanojoules, 5 kilohertz, 0.55 Na, and I put the gratings, the waveguides about 200 microns below the surface, and I did that basically by lowering the laser down while it's running until I see damage on the surface of the microscope slide, and then I zeroed the z-axis and then just plunged down 200 microns and started writing some planes. We fixed the rep rate, and I tried some different translation speeds. It's difficult to see much difference just by optical imaging alone like this. I think to really know the performance of these devices, we'd have to actually couple light through them. We didn't have time for that. And I tested some line-by-line patterns in bulk material just to see if I could produce nice grading structures, and we can. So it would be nice to go and see if we can actually write face masks or other sorts of transmissive grading elements using these techniques in bulk materials and see what the performance characteristics are that way. So there's all kinds of interesting stuff we can still do. I did some art as well. I wrote my name into glass. I believe the width of this is about 100 microns and the height being about 30. So this is a fairly small structure that you definitely cannot see with the naked eye in looking at the microscope slide. And so ultimately, we sort of have to ask the question of what's next. So the future work, I do want to study the difference of different wavelengths and the impact they have on this core confined damage. So when we say core confined damage, this is the fiber core here. And if we change, this would be at energy 2, and this is at energy 1, and energy 2 is greater than energy 1. We see that the damage can be constrained just to the core, so that there is some difference in damage threshold between the core and the cladding. And we want to know if we can exploit that so that we can write gratings only in the core, even though we're scanning beyond that region. So we think maybe wavelength may have an impact on that. We want to investigate more of the temperature characteristics, type 1, type 2, and maybe look at what the damage effects in the mid-IR are, and maybe take some electron microscope images. So that would be, we would take the fiber, okay, and here's the grading plane written through the center. And what we want to do actually is we want to polish this down, so that what we end up with is a structure that this is the core, this is the cladding, okay, and we want to look at that damage structure written into it here. And so then we can look at this under the SEM and see what that pattern looks like. We may have to etch this a little bit to kind of see the surface structure a little better, but we can play these sort of games with figuring out what the material looks like. Actually, right now we're working on a device to do computed tomography images by basically on this axis rotating the fiber and taking images, and then we can compute the computed tomography profile, and that'll allow us to have greater resolution and to take images of the inside of the material and see what the behavior of the refractive index modification is without actually etching and doing SEM imaging. So that would be very interesting to look at. Regarding the different wavelengths, depending on wavelength, we might be able to move from sort of a multi-photon ionization to sort of an intermediate regime. This is based on what's called the Keldysh parameter, and we can see that that the Keldysh parameter does change. So we're usually working around 1 micron here, which is at this point, right? If we move out to say 2.8 microns where our OPA is, we would in theory be out here, right? And out here we're looking at, a Keldysh parameter of, 0.1, so 2, 3, maybe 0.4, which would mean that we're looking at more of a tunneling ionization regime. So we want to know what the difference is in index modification if we're out in tunneling ionization, whereas right now we're probably in some sort of intermediate regime. So we kind of want to study this a little more and understand if there's advantages that can be had for using one regime versus another. We want to try writing some waveguides in interesting novel materials like silicon nitride, because we can build three-dimensional structures like are shown in this paper about single photon quantum contextuality. So there's some interest in looking at this. There's some interest at Carleton University for working on metamaterials and fabricating metamaterials by basically laser machining the surface structure. And of course, we want to investigate FBGs more. It's a vested interest, both my supervisor and I. And perhaps even look at building more sensors. So just writing Bragg Gratings, standard Bragg Gratings like we've shown here in this work, and using them to build specialty sensors for various applications. And as I mentioned here in May, but even looking at it now here in October, we're very close to getting a few papers out on some other topics related to Bragg Gratings, and we'll be excited to share that when that's available. So thank you very much. You can contact me at Carleton if you have any questions about this work. And I should always point this one out. A very special note, I'm very grateful to the support of my grandparents in all this work. A lot of it wouldn't have been possible without their support over the years. So I just want to say thank you to Ed and Maureen, my grandpa and Nan, for all their support over the years in all the work I've done. They've really been an inspiration in keeping me at it when sometimes it feels like it's impossible to get some of these things done. So thank you very much. And here are the references for this presentation. I do have a few extras, which I won't spend too long on, but this is effectively the impact of phase error or chirp. So when we were having problems with tuning, we were writing gratings that looked like this effectively. And what I think was going on was we were writing grating planes along the fiber core, but every now and again a grating plane would be slightly out of place. And so this distance might be lambda, but this distance is, lambda plus or minus some delta. And then all these other periods would subsequently still be lambda. This produces this error. So instead of seeing a nice sort of Bragg resonance that would look like this, what we end up with is this other sort of crap in the background. And so this is one of the problems we had. And so that was solved by increasing the fiber stability and by designing a better jig, and also by improving our stage tuning so that we have better position-to-position error. And so by sort of combining both of those together, I think we really improved the performance characteristics of our setup and our ability to write high-quality Bragg gratings. So it really goes to show that there's a lot of important components that goes into every piece of work, and you don't really know the importance of them until you've actually explored them. Anyways, I think that's where I'll leave this for now. Thank you very much for taking the time to watch this presentation. If you're viewing it and you've made it all the way to the end, I know this has gone on for about an hour now, but if you're here, thank you very much, and I hope you were able to get something from this that may help you in your research or may help you in your work. And if you're interested in any collaborative work or talking more on the subject matter, please feel free to reach out. I'm always happy to talk research and and explore what opportunities there are out there in the world. So thanks a lot.